Let me point out that if we eliminate 0 from this table, then we still get a table for perfectly good operation. That operation is still closed, because if we eliminate 0 here and here, no zeros appear down here. There's no way we can get 0 out of the numbers 1, 2, 3, 4, 5, or 6 on a 7-hour clock. Now that's not the case on a 6-hour clock. We see that on the 6-hour clock we get zeros all through here. But on a 7-hour clock we get no zeros from any number 1 through 6 unless we happen to combine that number with a 0. In that case we would get an operation by eliminating all the 0 from consideration. Eliminate 0 from the set itself, so we don't have any of the zeros. We would get an operation that's closed and has an identity of 1 and does have inverses. Every element would then have an inverse if we eliminated 0 from all consideration here. Now what we want to do is we want to look at the ideas of closure. Now for clock arithmetic, all clock arithmetic does have the closure property. All addition and multiplication, all clocks, no exception. Commutativity. All addition, all multiplication, and all clocks. Same as above here. The identity is always zero for the addition, 1 for all multiplication. This works on all clocks again. Again, the 0, when you put it together with something on addition, doesn't change that thing, and a 1 on multiplication doesn't change that thing. So in all clocks, you have these identities. There's this 1-to-1 property, and that's a property that's illustrated by the 7-hour clock. By 1-to-1, we mean for every row, every number appears exactly once. And that's not really a terminology that the text uses in this chapter, and we're not going to talk about it. Okay? The inverse property is always true for addition, all clocks. The inverse property is never for multiplication except if 0 is eliminated then it's sometimes the case. Now by sometimes we say for example, yes for 7, no for 6. 6-hour clock, you do not have the inverse property, because again there are many elements in the 6-hour clock that you can't combine with anything else to get the identity on multiplication. You can't get 1 in many of the rows and columns. Now let's talk a little bit about associativity. Okay, associativity again means for any operation, and let's just use some symbol, like how about an upside down triangle for the operation. This is what the associative property would require for all elements A, B, and C in the operation. For all possible choices of A, B, and C. Now that means that if you put A and B together first and then operate that with C, put that together with C according to the rules of the operation, you get the same thing as you do if you put A together with the result of putting B and C together. It says that the order or the grouping of the calculation doesn't make any difference. Now this is certainly true for multiplication. It's a familiar property of multiplication, and it's no surprise at all that if we did any numbers, 15 times 12 times 3.7, that we'd get the same thing as if we did 15 times 12 times 3.7. So that's an example of an associative property, and it's true for all real numbers. It turns out, since modular numbers are done by real number arithmetic, in other words, clock arithmetic is in some ways identical to real number arithmetic. We just do the real number arithmetic on a clock and then we get a remainder. That the same thing is going to be true. And it's always going to be true for numbers. Of course, we wouldn't do clock arithmetic with a number like 3.7. Clock arithmetic is strictly confined to integers. But there's an example of the associative property. And we'll look at that in terms of more abstract operations shortly.